Hello, everyone, and welcome to Precalculus. This is section 3.2 on logarithmic functions and their graphs. Logarithmic functions are inverses of exponential functions. The definition of a logarithmic function with base a is y is equal to log base a of x. Make sure you know how to pronounce that. Log base a of x. If and only if, this is a cool little way of writing that, if and only if x is equal to a to the y. So if you're in Precalculus CP, you're of course welcome to write this on your appendix. If you're in honors, you'll have to memorize it, but it's really actually important that you memorize it just so that you can be fluid with it and not have to always be looking at your notes. The key is that, like all inverse functions, the x and the y reverse. So notice here that the function is with the x, and then in reverse, the function is with the y. So the x and the y reversed their roles. Second, the thing to notice is that it's always base a. This is read log base a of x, and this is a base a with an exponent of y. So in both cases, the base is a. We'll do a couple examples to show you. So if you have log base 3 of 81, that is exactly the same as 3 to the 4 is 81. So again, what two things happened? The base is always the same, but the x and y reversed. So now the 4 is with the 3 and the 81 is by itself. This one has a base of 16. So it still has a base of 16. But now the 3/4 is with the 16 and the 8. So these two expressions are equivalent. Just like you guys think of x squared is equal to 4, that's the same thing as saying x is equal to plus or minus 2, square root of 4, which is 2. You know that square root and squares are inverses of each other, and that's how you solve them. So we need to learn about this inverse, which is a man-made function called log, so that we can solve exponential equations. Going from an exponent to a log, now it's going to be log base 9 of 27 is equal to 3/2. And log base 4 of 1 over 64 is -3. So this is usually a challenging section for people because they're just not used to the concept of the log. Use the definition of a logarithmic function to evaluate each logarithm at the indicated value of x. So I want f of 32. Remember, this notation means I'm going to plug a 32 in where there's an x. Log base 2 of 32. And you might be thinking, I don't know how to do log base 2 of 32. So off to the side, I think to myself, all right, log base 2 of 32 is equal to something. How am I going to figure that out? You probably can't. So you switch it to exponential. 2 to the something is 32. Do you know what that is? 2 to the 5 is 32. So this is equal to 5. That's what a log tells you. It tells you 2 to the what is equal to that number. F of 2 is equal to log base 4 of 2. And again, if you're thinking to yourself, I don't know how to do log base 2 of 4, I don't expect you to. I expect you to switch it to exponential form, to sit there and say, I don't know what that is, but I know that 4 to the something equals 2. Now this one's a lot trickier. I got harder on you. 4 to the what is equal to 2? What would make a number smaller? What kind of power? A fractional power. The square root of 4 is equal to 2. And what does that look like as an exponent? 4 to the 1/2 is equal to 2. So log base 4 of 2 is 1/2. F of 1. So they're saying plug in a 1 and tell me the answer. So I plug in a 1. All right, let's see if you can do it on your own. Can you think about that? it's saying log base 3 of 1 is equal to something. So 3 to the what is equal to 1? Hopefully you thought of 0. Anything to the 0 power is 1. And the last one, f of 1 over 100. That's what they want me to plug in. So I have log base 10 of 1 over 100. So again, I don't expect you to be able to do this. Log base 10 of 1 over 100. You're supposed to figure that out. I expect you to convert it to exponential form. 1 over 100. Now, last lesson in exponential functions, we learned that if they have the same base, you can make them equal. So 10 to the what is equal to 100 is the same as 10 squared. Still not good enough. But I can rewrite this as 10 to the negative 2. So this must be negative 2. So this log base 10 is I was about to say so common. That's exactly what it's called. It is called the common logarithm. So just like when you have 3x squared plus x minus 8, what number is in front of that x? There's a 1 there. You can't see it, but everybody knows there's a 1 there. Similarly, if you don't see a base with the log, if it just says log of 8, that is assumed to be 10. Assumed to be 10. That's how common it is. So instead of seeing log base 10, you're never going to see that. You're just going to see log. And it's also so popular, it got its own spot on the calculator. So if they want to know log, I'm not going to write base, of 10, or log of 1/3, or log of 2.5, it's on your calculator. So that button on your calculator is right here. So you literally can just say log 10, and it'll give you the answer. The first one is 1. Log, now I want to say 1/3. You can use alpha f1 to make the fraction, and then you can say 1 over 3. Make sure you go over, close your parenthesis, and it's negative 0.477. Log 2.5 in parentheses. It's that easy. Log negative 2. Now remember with the negative, don't use the subtract button. You'll get an error. Negative 2. Ooh, we still got an error. So let's talk about why. The key behind why you get an error is actually based on the inverse. So notice what they've put the log with. Just like the square root button is with the x squared button, the log button is with the 10 to the x. Now I know that I said you don't really need to write the 10 there, but just while I'm explaining it, I think it'll make more sense to have the 10 there. So let's talk about why a log base 10, or honestly a log base anything, of negative 2 would give you an error. Because if I reversed this, this is saying 10 to the what is equal to negative 2, right? And this is an error. There is no number that's ever going to make negative 2. Watch why. So if I pick 1, then 10 to the 1 is 10. If I pick 2, 10 to the 2 is 100. All right, you can see this is the wrong direction to go in, right? 10 to the 3 is 1,000. None of these are going to make negative 2. So let's go the opposite way. 0. 10 to the 0 is 1. Negative 1. 10 to the negative 1 is 1 over 10 to the 1. Remember, a negative exponent in the numerator is the same as a positive exponent in the bottom, which is 0.1. 10 to the negative 2 is 1 over 10 squared, which is 1 over 100, which is 1/100th. 100th, a penny. 10 to the negative 3. Do you see where this is going? This is going to become very, very, very small. But is it going to become negative? It's not. Think about the exponential graph. The exponential graph has a y-intercept of 0, 1, and once you get bigger, or positive, bigger than 0, the graph is going to go up. But as you become more and more less than 0, -1, -2, the number's going to get very small. It's going to get close to 0. But is it ever going to be negative? No. So since what logs do is tell you the answer to an exponential problem, since the answer to an exponential problem is never going to be negative, you can never take the log of a negative number. That's really the bottom line. Undefined. You can't take the log of a negative number. Okay? Don't forget that. Properties of logarithms. So just like I'm hoping that by now you know that any number to the 0 power is 1, similarly, if you ever have log base a of 1, it's always going to come out to be 0 because they're just inverses of each other. Log base a of a, if the base of the log is equal to the number that you're taking the log of, it's just going to be 1. And why is that? Because a to the 1 is equal to a. If the two bases match, log base a, and then of the exponent, you have a, of the exponential part, you have a to the x, it's just going to be x. Because, or not because, and if you ever have a to the log base a of x, that also is going to cancel out and just give you x. Think about it this way. If you have the square root of x and then you square it, it goes back to x. You've undone it. If you have x and you add 3, but then you subtract 3, you're back to x because addition and subtraction are inverses. If you have 2 times x and then you divide by 2, you go back to x because multiplication and division are inverses. Well, if you have an exponential function, but the exponent is a log with the same base, you've undone it and you're going to go back to x. And finally, if you have log base a of x is log base a of y, then x must be equal to y. So obviously these are properties that you need to memorize if you're in honors and add to your appendix if you're in college prep. So let's use those to actually do some problems. So right away, log base 4 of 1, just pretty much any base, it's always going to be an answer of 0 because 4 to the 0 is 1. Anything to the 0 power is 1. So this piece right here is always the answer to the exponential problem. So you're always asking yourself 4 to the what will make 1? Well, to the 0. This one, I have a base, and then I have this, and they're the same. So think about this as square root of 7 to the 1. This base and this base, if they match, then the answer is just 1. And in the other direction, this is the base, but then it has the same base here. It just cancels out and gives you 20. Takes a little while to get the hang of these. Using our one-to-one property, as long as they're both base 3, we can go ahead and set them equal to each other. X must be 12. You can probably do the next two on your own. The answers are -1 and plus or minus 4, but I will do them out. Because these are both, anybody know? Base 10. Because these are both base 10, 2x plus 1 is equal to x. I'm going to subtract the x from both sides and subtract 1 from both sides. On the last one, they're both base 4, so I can set them equal to each other. I don't have an x term. Normally when I see an x squared, I set it equal to 0 and factor, but if there's no term with just an x, then you can take this shortcut of getting the x squared by itself And then using the inverse function, which in this case is square root, to find your answer. Don't forget your plus or minus. Otherwise, you only get half the answers with only half the credit. Let's move on to graphing. So the first key is to know the basic shape. You may remember when we studied inverses that if we had a parabola, that the inverse was the square root. And that one of the ways we knew something was an inverse was because it was reflected over the line y is equal to x. That's still going to be true. Now we're looking at exponential functions, and we're trying to reflect them over the line y is equal to x. So they're going to end up looking like this. All right, I'll draw it all by itself just so you have a graph of it by itself, but I want you to see where it came from. So this is the graph you need to have in your head. When you see log, you need to be thinking it's going to come out like that. Notice that its domain is just the positive numbers. Remember, you can't take the log of a negative number. So it's going to start at 0 and go up to infinity. You can't take the log of a negative number. Its range, however, will just keep going down, and even though it gets a little slower, it does keep going up. So the range is all real numbers. The y-intercept, there's none. It doesn't cross the y-axis. Just like our exponential function didn't cross the x-axis. Remember, they're inverses. And our x-intercept, do you remember how this one was 0, 1? Guess what this one's going to be? 1, 0. So it's always going to cross at 1, 0. And again, that just reinforces because log base a of 1 is always going to be equal to 0. Just like any number to the 0 power is 1. That's why that was always our spot. Now, the log base a of any 1 is always going to be 0. It does have a vertical asymptote. X is equal to 0. So right along this line, doesn't cross it. Now, even though it does flatten out, it may look like it's going to eventually have a horizontal asymptote. It does not. There is none. Here is the fantastic thing about math. If you have an x minus c, that is going to shift it right, just like always. If it's an x plus c, it's going to shift it left. By the way, it also shifts the asymptote because it's vertical. That's going to move with it. If you have a plus c on the end, if the c is positive, it's going to move it up. And if the c is negative, it's going to move it down. This is not changed from any function we've studied all year. And similarly, if you have a negative x, that is going to flip it over the y. So it would start there, and then it would end it right there over the y-axis. But just like you're used to, if there's a negative out in front, you remember that if you had an x squared equation, right? But if you have a negative x squared equation, you would expect it to do something down, right? So same thing. A logarithmic graph normally looks like this, but if it's negative, it's going to flip it upside down. So here's the key. Literally, cannot stress this enough. You are never going to try to graph a logarithmic function as a logarithmic function. You are always going to change the equation to exponential form first. I will show you. So I don't even attempt this. Never attempt it. I just change it. So this is y, right? Y is equal to log base 2 of x. I'm going to change the form. 2 to the y is equal to x. These two mean the exact same thing. I've just changed the way they look. It would kind of be like if I said y is equal to x squared. If for some reason I didn't want to graph that, I could graph this plus or minus the square root of y is equal to x. I'm not going to do that. But these two mean the exact same thing. They just look different. So that's what I'm going to do. I'm going to make a table of points because I'm good at this, but you have to be careful. You're going to plug in for y. So when y is 0, 2 to the 0 is 1. When y is 1, 2 to the 1 is 2. Do you recognize these numbers? This is what we just did with exponential functions. 2 squared is 4. You could do a -1, but it's not going to be easy, right? 2 to the -1 is 1 over 2. So let's go ahead and plot them. 1, 0, 2, 1, and 4, 2. Which, if you didn't have the 1/2 -1, you might just think that it was like a square root function. But it's an exponential, or it's a logarithmic function. So remember that you should know the shape. It's going to look like that. It's going to have an asymptote, and then it's going to come up and go like that. That's what it looks like. It is the inverse of the exponential function. Okay, so here's my giant warning. Only do exponential function of the parent, then shift. So I wouldn't try and switch this whole thing. I would just say, okay, it's a base 4, then I'm just going to do a base 4. X is equal to 4 to the y. So I completely ignore that -3 there. I think of this, I just think about it being y is equal to log base 4 of x. Do the shifting afterwards. So I switch it to be x is equal to 4 to the y. Remember, the base always stays the same, but the x and the y switch. And I make my table. Don't forget that you're going to plug in values for y, just because it's easier. So if y is 0, anything to the 0 power is 1. If y is 1, this would be 4. If y is 2, we're already up to 16, so I'm not even going to try and graph more than that. And if you know the shape, 2 points should be enough. 1, 0, and 4, 1. It's going to have an asymptote right along the axis, and it's going to look something like this. I did it dotted because this isn't my final graph. So I'm going to shift it, everything over 3. So I just wanted to show you what it looks like. So I don't want to leave that on there. I think it'll get too cluttered. So my new origin doesn't go up or down. It just goes 3 to the right. So this is my new origin, which means on a logarithmic function, that's where my asymptote is going to be. And then I pretend that that's my new origin. And now I do the 1, 0 and the 4, 1. 1, 1, 2, 3, 4, 1. So it's going to look like this. Okay. So you could draw the original on there and then actually physically shift it, but it could start to make for a kind of messy graph. So personally, I just shift my whole origin. All right, we got 2 more graphs here. Again, only do the base function. So this is y is equal to log base 5 of x. Don't worry about the -1 and the +4 until afterwards. So I'm going to switch it to exponential form. So x is equal to 5 to the y. The base is still a 5 in both cases, but now it's y and x have been reversed. You have to plug in numbers for y. So y, anything to the 0 power is 1. If y is 1, 5 to the 1 is 5. I could do 2 and 25, but I'm not going to be able to graph that. But before I actually graph it, I'm going to move my origin. I'm going to go 1 to the right and then up 4. 1 to the right and 1, 2, 3, 4. That's going to be my new origin. So for a logarithmic function, the asymptote is right on the y-axis of my new origin. And then I'm going to plot my couple points here. 0, 1, and 5. 1, 2, 3, 4, 5, 1. And it's going to look like this. There we go. So on this one, it has a negative out front, which means it's going to flip it upside down. The base you can't really see, but it's a 10. You do have to kind of write it in if you want to reverse it. So 10 to the y is equal to x. I don't know why I made that so long. I'm only going to do 2 points. If y is 0, anything to 0 power is 1. And if y is 1, we're already up to 10. We're barely going to fit it as it is. This one does not shift left, right, up, or down. So this one still gets to stay at the origin. That is going to be my origin, which means my 2 points are going to be 1, 0 and 10, 1. And it would look like this, except that it has a negative. Now remember, a negative out in front. Think about what a negative out in front does to a square, just a square function. It flips it upside down. So we're going to flip this upside down. You can't flip this point. That point is already on the axis, but you can flip this one to down here. So it's going to come down and then it's going to go like that. And its asymptote doesn't move. So its asymptote is still right along the line, but it got flipped upside down. All right, that's it for graphing. The natural logarithmic function is defined by f, oh, I don't think we want that anymore. F of x is equal to log base e. So we introduced e last time. So it was called the natural base. Now it's called the natural log. But it's so famous, it has its own unique way of writing it, which is ln of x. That's how we actually pronounce it, ln of x. I know that seems funny. It's the natural log. Why didn't we call it NL? It was discovered by somebody in France where they reverse their adjectives with the thing it's describing. So I guess log natural, but it's backwards. So ln of x. So the natural log button is right here next to the 4. You'll notice that it has the e to the x as the matching corresponding part. That's because they're inverse functions. So I'm going to type in natural log of 2, and that first one is 0.693. I'm going to type in natural log of 0.3. Your calculator doesn't need you to do that 0. And get negative 1.2. Natural log of negative 1. Aha, we have an error again. Why do we have an error? Because you can't take the natural log of a negative number. And on number 4, natural log of 1 plus, so to make your calculator do root 2, second x squared, and then the 2, use the arrow key to get over, and then do your parenthesis, 0.881. So just like we had properties of logarithms, we have the same exact properties for natural logarithms. The natural log of 1 is equal to 0. If you think about this as log base e of 1, does that help you a little bit? Remember, log of 1 of any base is going to be equal to 0. But why is that? Because e to the 0 equals 1. Remember, this is always the answer to the exponential problem. So e to the 0 is 1. Natural log of e is 1 because, remember, think of this as log base e of e, because the exponential problem is e to the 1 is equal to e. So you would never hesitate. If I said to you, what's e to the 1? You'd just say it's just e. The 1 doesn't matter. Well, similarly, the natural log of e is easier to see that the two e's cancel, but natural log of e is just 1. Natural log of e to the x simplifies to x, and e to the ln of x simplifies to x. And as before, if the two bases are the same, which these are, this is log base e, and this is log base e, then x must be equal to y. So how do we use these properties? Well, you can't really use it in this format, but if I switch this to e to the negative 1, then I have it from up here that ln of e to the x. Think of ln and e as canceling each other. Like on your calculator, they're together for a reason. They're inverse functions. So they literally cancel and just leave you with negative 1. Natural log of 1 is 0, right up there. And 0 divided by 3 is 0. E to the ln of 5, the e and the natural log cancel each other. So you end up just with a 5. It's not an exponent anymore. It's back down on plane, you could say. And the natural log of e, this is equal to 1. So this is 2 times 1, which is 2. You definitely want to practice these. It's not intuitive. Find the domain of each function. I know each chapter you keep thinking this is going to go away. It's just not. So domain, remember, you can never take the log or natural log of a negative number. So that means that this x minus 2 has to come out to be greater than 0. Okay? So we add 2 to both sides. X is greater than 2. You can write it like that, or you can use interval notation. In this case, it's 2 minus x that has to be greater than 0. So you can subtract 2 from both sides, but don't forget that when you divide by this negative, you have to reverse the inequality. So this actually becomes x is less than positive 2, which in interval notation would be negative infinity to 2. It's always great to check your answers. So if this is true, then 0 would work. And does 0 work? Yeah, natural log of 2 minus 0 is natural log of 2, which is not negative, so that's good. So a little bit of a trick here. Natural log of x squared. Well, x, when it's squared, will come out to be positive. So this domain would be all reals, because you can take the log of any positive number. The word problems in this section you're going to like. They're very straightforward. Even though it has a lot of words, the actual problem is pretty simple. Students participating in a psychology experiment attended several lectures on a subject and were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores for the group are given by the human memory model f of t is equal to 75 minus 6 natural log of t plus 1. T is only good for 0 to 12. That's the domain. So in other words, they decided that this model only worked over the 1 year. What is the average score on the original exam? So they learned something, they took an exam, so at the beginning. So we're going to put in a 0. 75 minus 6 ln of 0 plus 1. 75 minus 6 natural log of 1. Now, do you remember? Natural log of 1 is 0 because something to the e to the something made 1. That something must have been 0. So this is 0. So it's just 75. So the average score was a 75%. But what about at the end of 2 months? And then what about at the end of 6 months? So at 2 months, you're going to put a 2 in there. 75 minus 6 natural log of 2 plus 1. So I won't switch to the calculator page. It comes out to 68.4. And then at the end of 6 months, f of 6 is equal to 75 minus 6 ln of 6 plus 1, which again, I am sure most of you are not bothering to get out your graphing calculator. You're just going to wait and see. All right, that concludes section 3.2. I hope you have a great day.